Welcome to this episode about T1.cont, the continuous timing analysis and supervision for your embedded system. What makes T1.cont useful? Well, T1.cont monitors events in real time on your target. In other words, whenever something important happens in your embedded system, T1.cont is live at the scene. You do not need to connect T1 host software for T1.cont to work. You only need it to view the results, or if you want to fine-tune T1.cont's behavior on the fly. T1.cont will calculate timing statistics, monitor system health, and trigger customizable function callbacks. You get to choose why and when. Let's take a look at T1.cont in action using the AT demo application on an Infineon Oryx microcontroller. T1.cont information is prominently displayed in the T1.cont table view, although it is also available in other places. You can export the information for reports and custom post-processing if you like. The T1.cont table view contains two main areas: System Overview and System Elements. System Overview provides you with a high-level view of systems, usually CPU cores. On the left, you see the current CPU load, as well as the minimum and maximum observed CPU load per core. The range of values so far observed is also marked in gray. The high CPU load threshold is marked by a red flag. Should a system reach the CPU load threshold, a reaction through customizable callback function will be triggered. T1.cont status flags are located to the right of the CPU load display. Here you can find the T1.cont internal status and global settings. Now, let's turn to our example at hand. Core 0 contains a simulated gasoline engine. Using the little triangle, you can expand the view for Core 0 and get a detailed description of the status flags if you desire. So far, the observed CPU load was somewhere between 52.6 and 55.8%. Current CPU load is around 53.5%, and we are far away from the red flag where a reaction will be triggered. That flag, of course, can be moved. System Elements provides more details about what is happening on the cores. Looking at Core 0, we can see the runtime of a simulated gasoline engine. In our AT demo application, the variable task on Core 0 is running in sync with the simulated engine rotation. Currently, T1.cont calculates the core execution time, short CET, of the task, which tells us how long one instance of this engine management code runs. Let's see what happens when we rev up the engine. As the engine RPM changes, the CPU load moves a bit, but core execution time does not. Apparently, the engine code takes the same amount of CPU cycles to run through, regardless of engine speed. But running it more often per second puts a higher load on the CPU. Let's put the engine back to its 800 RPM idle speed and set up a better observation. T1.cont allows us to change the kind of analysis it performs on the fly. In this case, it is helpful to switch the analysis of the variable task to show delta time, dt. Delta time is the time between two runs or instances of the task. Currently, the hardware display shows 800 revolutions per minute, which translates to 13 1/3 revolutions per second, or 75 milliseconds per revolution. If we rev up the engine again, the changing delta time and its impact on the CPU load become obvious. So far, so good. The system does not exceed 62% CPU load, and it looks rock solid. Let's return the engine to its idle speed of 800 RPM and reset the variable task results using the associated icon. Now that we can see the variable task's delta time, let's increase the core execution time of the periodic 1 millisecond task using a feature called T1 delay, which will be discussed in more detail in a different episode. We will increase the core execution time of this task by roughly 10%. Which shouldn't have a huge impact. And indeed, we see the current CPU load is hardly impacted. All is well. Let's rev up the engine, but this time slowly and manually. Ouch! Something went seriously wrong. But at least T1.cont froze the trace buffer for us. So by downloading the trace, we can see exactly what happened in T1 scope. This is a recommended workflow. T1.cont captures and T1 scope explains. The explanation is the variable task pushes the 1 millisecond task back in a certain situation that in this case also involves the 25 millisecond task. Then, and only then, the 1 millisecond task violates its period, leading to an activation failure, which T1 scope duly records and stores for us to download and observe. The engine RPM at which this happened was still rather low, below 1000. And the CPU load number never gave us a warning that something was amiss. Luckily, T1.cont can help us detect this kind of problem while it is still developing. AutoSAR defines a timing parameter, slack time, short ST, which serves as an early warning indicator for activation failure. When slack time reaches 0, activation fails. T1.cont can calculate and supervise slack time. We've reset our ECU and started from the beginning, and will now set up a slack time measurement in T1.cont for the 1 millisecond task that gave us trouble. Here we are, and the slack time looks good at a minimum of about 360 microseconds, which is 36% of the task's period. Many companies set a lower limit of 10% in their requirements, which is 100 microseconds in our case. Let's see what happens when we rev up the engine again. Alright, we've learned that from the get-go, the system was less stable than it looked, already violating the common 10% ST rule. That is good to know. However, a human watching the slack time for hours will grow very bored. Luckily, T1.cont can watch it for us and report back by means of a callback function. here we are. A little red flag is introduced, which triggers a measurement halt. And when we download the frozen trace buffer, we can see that indeed we have found the same situation, only this time before the activation failure occurred. And the point where it happens is marked as a constraint violation. T1.cont informs us of constraint violations by means of a callback function. The callback ends up in a clue layer function, which is provided in source code. That allows you to react to the situation in any way you want. In the AT-demo project, the constraint violation callback function simply sets a stop trigger on all cores, but that can be extended in any way the user desires. T1.cont features several callback functions for different reasons. The callback that you just saw is the constraint violation callback, but there are also callbacks for CPU load and T1.cont error conditions. The CPU load callbacks also provide you with the raw numbers that you need to calculate the current CPU load on the fly for post-processing in your own software, or simply to display them somewhere where it's visible to the user. Another highly useful feature of T1.cont is focus measurement. Putting a focus on something tells T1.cont to determine timing parameters with a maximum level of detail available. It applies to one system element and one timing parameter. I've restarted the ECU and set up everything fresh to show you a focus measurement for core execution time on the variable task of our gasoline engine. We get a min, max, and average core execution time, as might be expected from a CET focus measurement, but also an average delta time. And with these two pieces of information, T1.cont can calculate the focus CPU load, which is a good approximation for the fraction of total CPU load on this core caused by the very task we are currently observing. Which very often is the kind of question we want answered, especially with variable things like RPM-dependent tasks. And as we can see, the focus CPU load is changing significantly with the engine RPM. Even better, T1.cont focus measurement is not limited to a single item at a time. In fact, T1 supports 2 independent focus measurements per core, bringing the total number of concurrent focus measurements available on this Infineon Oryx up to 6. Focus measurements provide detailed insight into the timing behavior of critical tasks, interrupts, and runnables, and especially when combined with T1's powerful measurement automation features, become a pathway to systematic understanding of your ECU timing. This was a short introduction to T1.cont. I mentioned several timing parameters, and if you would like to know more about these, there are 2 options. First, the book Embedded Software Timing describes them in great detail and with examples and how-tos. Alternatively, you will find an overview on our timing poster, which you can download for free as a PDF. Or you give us a call and we will be happy to send you your own hard copy. T1.cont is only one component of T1, so check out the other episodes to learn more about how T1 can help you to efficiently develop safe and reliable embedded systems.